you can get something nice to drink and make yourself comfortable. Here next to me is Manuel, our CEO from TLK Energy. And over there, you can see Raphael, who's a simulation engineer here. Yeah, we sit here in our conference room. Behind, you can see a SpeedGoat test setup. And yeah, we hope that slowly everybody gets into the webinar room and we can go along with the content. As mentioned earlier, today we're diving into TIL Goes HiL, and we hope that at the end of the webinar, you understand that why it's a good idea that TIL, the model library for thermal systems, goes HiL hardware in the loop. You may have wondered why hardware in the loop testing is widely used in the automotive industry, but hasn't been adopted for heat pump testing yet, or for other thermal systems. Well, we believe the time is now. In this webinar, we'll give you a comprehensive overview of the entire tool chain for efficient testing of thermal systems. To demonstrate this, we'll use a heat pump with reversing valve as an example model and look at the testing of a defrosting controller. Manuel Gräber from TLK Energy here will start with our motivation and address key questions like why TIL. Afterwards, Konrad Beser will introduce you to the FMI standard and explain how it can be applied for HiL testing. Then Raphael Hornung will walk you through a practical example showcasing the benefits of controller design using simulation models, and we'll see hardware in the loop in action. To make sure we pack as much valuable content as possible, we've pre-recorded parts of this webinar. This way, you won't have to wait for real-time simulations to run. If you have any question during the webinar, as I mentioned before, please use the Q&A section in the top navigation bar. At the end, we will have time to answer some questions and have a little discussion. Also, again, I would like to mention that the webinar we record the webinar, so you can also have the video if you're interested. Now, let me hand over to Manuel.
Yeah, thanks, Lina. Yeah, for introduction, I prepared some slides. Let's jump directly into it. First, some naming conventions, which is sometimes confusing if people are new to this area. So we talk today about hardware in the loop testing, but hardware in the loop testing, I would say, is one tool as part of a larger topic. And this larger topic, I would name it model-based control development or model-based control design. I would say this means pretty much the same. And this model-based can cause some confusion, this term model-based, because actually if we look here on the left on a control loop, so we have two parts. One is the controller and the other one is the blend. And if people talk about model-based control design, model-based control development, sometimes it means model of the controller, but other people talk about it and mean model of the blend. So we at TLK, we typically more concentrating on the blend modeling because that's our daily business. But really can mean both. And both things make total sense. And in ideal world, if you think about improving your control design process, just do both of it because both makes perfectly sense. Using here, you can see an example in a signal-based model of a controller. In this case, it's a PID controller, graphically represented in a block diagram. It's signal-based, makes sense for control development. And here you see what we typically do, and also will be part of this webinar today, a model of a plant. In this case, it's a heat pump, air-to-water heat pump. You see here in graphical representation of a model. And the first recommendation from us from the last years we working on these topics, for these systems, equation-based approaches make very much sense. So I really recommend using signal-based approach for controllers. That's perfect for that. But equation-based things like Modelica language, what we are using, or Simscape, which is part of the MathWorks ecosystem, or GPROMs. So there are different equation-based tools and languages around. And for this kind of systems, physical blend models, it's much easier with these tools. The next slide. Here I would give an overview about the timeline of a typical control development project. So if you design a new control system for, let's say, a heat pump, you would start first with the basic concepts. That's really about trying out different control concepts, single input versus multiple input controllers. Should I use gain scheduling? Where should I place sensors? Is temperature sensor better than pressure sensor? Whatever. So these are these typical questions. And in this phase, modeling simulation makes very much sense because it's very easy to play around, try out different ideas. And usually the first idea is not the best one. So yeah, use models and play around with it. You learn a lot about the systems and you end up with better concepts. And for this phase, you need a blend model, of course. And one guiding idea about a good development process is to reuse this blend model through all the stages. In real world, in large companies, I mean, there are different departments involved, different modeling tools might even be involved. And I think there's a lot of work done twice or three times because in the end, models are developed again and again. And I think, it's easy to imagine that reusing blend models, it's a good goal. Still might not be easy in larger teams, larger companies, but this should be at least a goal for this process. The next step would be to, think about the details or add the details around a given concept. So I would think about, really adding state machine things, for example, add some error, failure stuff around it, some protection stuff, and really doing all the details for a real control system. Then this, in the ideal process, is also done graphically, for example, in Simulink or Stateflow, both of them. And in the end, if you have the detailed control design, of course, it's very important then to use this model also to generate C code out of it. So, I mean, in some industries, it might still be common. Once you have the detailed control design, you write it down piece of paper, hand it over to another department or even another company. They write C code by hand or PLC code, whatever, and give it back to you. And that's also one idea about model-based control design. Use the model, the graphically implemented model of your controller, and then generate C code out of it. And, I mean, production C code that really runs on the target in the end. This whole ideas, the whole tool chains in some industries, I would say it's quite established. So automotive, aerospace industry, that's maybe where all these ideas are coming from and are used and established. But in our area for thermal systems, it's still, there are some companies that are ahead and using some of these things or many of these things, but still there is lot to do. So I mean, I guess you are interested in this technology, and there's a lot of place to prove things and use it, adapt it to your workflows. But the key in the end is, of course, you cannot reinvent the wheel every time and do everything yourself. In the end, you would rely on established tools, and that's mainly software, but also hardware. And from the last years, where we have done many versions in this area, I would say this key technologies that we're using in our projects and customers are also using, these are the four most important things. Let's start with MathWorks software. yeah, that's mainly the software you would use for model-based control design. It's very established, well-known. I guess you all know it. Simulink and Stateflow are great for graphical control modeling, state machines, and Simulink block-based controllers. Then you have the coder products to generate C code for all kind of targets. In PLC coder, you can even generate code for different PLCs. Or embedded systems, so there are many different targets available. And the third part, which is also part of the MathWorks software box, Simulink Test, which we mainly talk about today. I mean, we don't use Simulink Test that much, but in the end, what we do, modeling for testing, in the end, you would use Simulink Test a lot for hardware in loop, modeling in loop, software in loop testing. In short form, it's called HiL testing for that. If you want to run hardware in the loop tests, in the end, you connect your blend model running on a real-time target with a real system. And of course, you could also use your PC with some I/O boards for that, but typically you would use dedicated real-time machines for that. And that's where Speedcode comes into play. So they are MathWorks' daughter, and you can get all the hardware from them, which is perfectly integrated in the MathWorks tool chain. And we will also see this today in detail how it works, but you can really deploy models on the blend models on the Speedcode hardware for hardware loop testing. You could even do it the other way around and deploy control models to the Speedcode systems. Then you have it's called rapid control prototyping. So we have a very fast process to test out new control ideas at your labs. From our side, of course, very important thing is our TIL suite libraries. So these are the model libraries we're using in our daily work, not only for HiL applications, many different things. I guess many of you are already using TIL or at least familiar with that. So I don't want to talk too much about that. I would say the main benefits when it comes to hardware loop is you need robust and fast models. So if you run automatic tests overnight, it's not good if this model fails or it's not fast enough. So I would say that that's the key for HiL. And when we talk about two-phase flow, including flow reversal, like we also will see again today, that's quite tricky. So I would say, our TIL models and also our experience how to do these models, it's quite unique, and it's still really challenging to get these models running fast and robust. But as you can see today, we know how to do it after many years of working on that. And we also have quite some customers using this successful. And of course, that's an important part of our tool chain today, our model libraries. And then there's a fourth thing I added because I mean, TIL is Modelica. The other part is MathWorks software. They don't really speak that well together directly, but there is some great technology developed during the last 10 years or maybe even less. I still imagine the time before we had this interface. It was really very time consuming. And now we have this standardized functional mockup interface, FMI. This is greatly supported by MathWorks, mainly the Simulink. You can import models, and it's also then all the way from Simulink to Speedcode target. We'll talk about this later in more detail. And it's really one key enabler for us to support customers like you with really best-in-class blend modeling tools to connect them with the best-in-class control development tools. Just a few details about background about the TIL library. It's component library for models. You can graphically or code view connect system models like heat pumps. It's mainly used in automotive industry, HVAC, aerospace, maybe some others, but I would say these are the most important industries. It's quite established doing that. It also has some very historical background. So it started with in 97 with first simulation models in C code. The switch to Modelica was some around 2006. And then you can see it matured over time with these major releases. Personally, I entered the TIL team at this time, as I remember this 2.0 release. I personally worked a lot on this library during that time. And yeah, now it's continuously improved. Also see the logo adapted a little bit during time. And yeah, still maintained. We will add models and use it ourselves in projects, and a lot of customers using that. Also, since 2017, we have a cooperation with Dassault Systems, and it's sold their different name. This might change in a couple of months, but currently it's a different name, TIL Systems, sometimes confusing. And yeah, so that's cooperation with large software company in this area. There are also add-on libraries available. So until we have the basic core models, and from time to time we take some models we developed around that and put them in and ready to use software product. And these are currently the products we offer. So it's application specific, for example, automotive models, hydrogen models. For heat pump manufacturers, maybe this heat storage and PCM storage might be the most interesting ones. And we also have an absorption add-on, which recently gained a lot of attention for direct air capture, taking CO2 out of the air, which is quite trending. Yeah, now the final slide before we really deep dive into technical parts. I present you here the blend model we use today in this webinar. It's an air-to-water heat pump with propane. So you can see the evaporator, fan, and then here is some blade heat exchanger condenser, heating some water, and compressor. Maybe the special thing here is, or not special thing, but we'll see this later. It's a suction side separator to store refrigerant. And in the end, we want to also look at defrost situations. That's why here is a four-way valve included to reverse the cycle for defrosting or for cooling applications. This other valve, you can forget it. It's not there in real world. It's only used to some trick, so we can have the state point sensors to get the pH diagram right in reverse conditions. So don't forget the cycle. Don't need it. And you also see a lot of signal conditioning around it. That's mainly for our HiL test. So we grouped actuator signals and sensor signals in one expandable connector in Modelica. And then we added some conditioning like limiters for very sensitive things like the valve, compressor. We directly added here. And we also added some unit conversion and some smoothing of signals with a first order element, because that's it's one recommendation already. This greatly improves robustness if you filter some very transient system. You can also download this model for free on the GitHub repository. It's published there. And yeah, of course, you need a TIL license to run it, but you can, if you have it, you can download this model there and try it out yourself. Okay, then I would hand over to the technical parts, and later we will discuss again about your questions.
Hello, my name is Konrad and I work as a simulation engineer at TIL Energy. When we want to make our Modelica models available in non-Modelica tools, we rely on the FMI standard. In the following minutes, I would like to give you a brief overview on what is behind the FMI standard, and then show you how to export a TIL-based Modelica model from Daimler as an FMU. So, what is FMI and what can it be used for? Let us look at the example as outlined over here. In our example use case, we have two suppliers that deliver models for specific components of a technical system. Each supplier uses a specific modeling tool and maybe even a specific solver, suited best to the specific problem. In our example, supplier 1 is using the TIL library and supplier 2 is using MATLAB. On the other side, we have a systems engineer. He or she has to deal with multiple suppliers, but uses a completely different tool, Python in this case. But still, he or she wants to simulate the component models either individually or even coupled in a co-simulation. And that is the point where FMI can help. The suppliers can export their models according to the FMI standard, and the systems engineer can later import them into his or her own environment and work with them. So to summarize, FMI is a tool and even platform-independent standard for exchange of dynamic simulation models. To give you an idea about the relevance of the standard, let's have a look at the web page. We see more than 200 tools listed here, and I bet there are some tools that you recognize. If we go to the main page, we also see some names of famous FMI users here. A simulation model exported according to the FMI standard is called Functional Mockup Unit, or FMU. It can be seen as a containerized model because also in the container the interface is at least as important as its content. Technically, the FMU is distributed as a zip file. That means that we can have a look into it and see if all the files are where they should be. The model representation works either with binaries, in this case they are platform specific, or with C code that is platform independent and can be compiled later on into binaries of the platform where the FMU should be simulated on. So it gives a lot of flexibility. There are two important FMI types that you should know. In Model Exchange, the FMU contains the model, but the solver must be provided by the importing tool. This leads to a complex interface. In co-simulation, on the other hand, the FMU contains both the model equations but also the solver. The advantage of that is that an FMU supplier can select a suitable solver that works perfectly for the model that he or she developed. And the person who just wants to simulate the FMU with the importing tool doesn't have to care anymore about selecting a suitable solver. This is probably one of the reasons why co-simulation FMUs are more common in the industry. But still, there are some important use cases for model exchange FMUs as well. When we want to export our Modelica or TIL model as an FMU, Daimler offers a lot of options. First of all, we have to select the FMI type. We can choose model exchange, co-simulation, or both. If we choose co-simulation, we also have to select the solver. In our case, we usually work with variable step size solvers. So, for example, we could use the Dussel solver for FMU. In this case, we would select co-simulation using Daimler solvers, and we would have to make sure that Dussel is selected in the simulation setup in Daimler. An alternative solver would be CVODE, which can be selected just like in the screenshot. And contrary to the Dussel solver, CVODE is also available for source code FMUs. The next important thing is to select the kind of model representation. I'm running Daimler on Windows here, and if I want to simulate the exported FMU on Windows, we can select Windows binaries over here. Daimler also offers the possibility to cross-compile binaries for Linux. This can be selected here. The last and strongest possibility is to export the FMU as a source code FMU. This can be done here. With the source code FMU, we can compile binaries for a specific platform later on. A typical use case would be if we want to use our model as a plant model in hardware-in-the-loop testing, and you need to compile specific binaries for your real-time machine. Under the model description filters, we have the option to decide not to export all our variables to the importing tool. For example, if we select the black box option here, the importing tool would only see inputs and outputs of the model. Finally, I want to share a personal recommendation for the model identifier. The default value that is set here is derived from the package hierarchy in Daimler, and it can be a very long name. But this model identifier is not only the initial file name for the FMU, but it is also hard-coded within the FMU. Therefore, I would recommend using a short name here to make sure not to run into any problems when importing the FMU to another tool. In the end, let's talk about licenses. For Daimler, a standard configuration license is sufficient if we want to export an FMU and run it on a computer that also holds a Daimler license. If we want to run the FMU on a system without a Daimler license, we need the Daimler binary model export license. And if we want to export a source code FMU, we need the strongest Daimler license, the source code generation license. Note that this also includes the binary model export. In TIL, binary model export is always included. We just technically need a small tool, the FMU configurator, to embed the license into the FMU. And also for TIL, if we want to export a source code FMU, we would need a special variant of TIL Media, the TIL Media source code variant. Now we want to make our TIL-based heat pump cycle model available as a planned model for controller development and hardware-in-the-loop testing in the MATLAB Simulink environment. To do that, we are going to export it as an FMU from Daimler, which can then be imported into Simulink. To prepare our model for the interaction with the controller, we are using interface. In this case, these interfaces are of the Modelica type expandable connector, which provides a good opportunity to group model in and outputs. Via the actuators interface, we apply the controller output and also boundary conditions like the ambient air temperature and humidity onto our heat pump model. In the sensors interface, we collect measurements that can be processed by the controller and easily monitored in the simulation tool. As VLE medium, we choose spline data, as this is available for source code export and also improves the performance of our simulation model. Let's get to the FMU export. To simulate our planned model on the speedcode real-time machine, the final FMU needs specific binaries. These cannot be cross-compiled with Daimler directly, but in MATLAB using a Simulink real-time method. That's why we need to export a source code FMU from Daimler in the first place. From the Daimler point of view, this requires the source code generation license. From the TIL point of view, we need a source code version of TIL Media. With these requirements fulfilled, we can now move to the FMU export options. As just discussed, we need to include the source code into our FMU. Additionally, we need Windows binaries to import the FMU into the Simulink model. In the end, let's talk about the solvers. We want to export a co-simulation FMU, so we need to select a suitable solver. Refrigeration cycles with their two-phase flow are highly nonlinear and challenging for numerical solvers. Initially, we used the fixed-step Euler solver. While it provides deterministic CPU times, it struggles with the nonlinearity of thermal systems. Extreme operation conditions, that are naturally the most interesting cases for controller testing, require very small time steps, making it hard to meet the real-time requirements. Even with model-specific adjustments and a lot of manual work, 100% robustness was never achieved. That's why we switched to CVODE, a variable step size solver. It does not guarantee upper bounds on CPU times, but handles nonlinear and stiff models much more efficient. For thermal systems where controllers run at low frequencies, like 10 Hz, the flexibility of CVODE is key. By using CVODE, we achieve the reliability that is required for automated controller testing. So let's select it in the export menu. Finally, we choose a short model identifier to avoid any problems in the importing tool. We can call it heat pump demo and start the FMU export. After the FMU export is finished, personally I like to perform a quick check on the exported FMU with FMPy. FMPy is an open source Python package for FMU simulation. It comes with a nice graphical user interface that helps me with my FMU check. After opening the FMU with FMPy, we see a nice overview over here. We see that our FMU includes the C code and also Windows binaries. Below we see the model in and outputs. As we have the Windows binaries included, we can just perform a quick test simulation directly in FMPy. This worked successfully. To check the source code, we can cross-compile Linux binaries with FMPy. This was successful as the Linux binaries just appeared here under the other platforms. After these tests, we have a good indication that our FMU can be used for hardware-in-the-loop testing on the real-time computer. Now that we have exported our TIL-based Modelica model of the heat pump cycle as an FMU, we can pass it to my colleague Raphael. He will use it as a plant model for controller development and hardware-in-the-loop testing. Thank you for your attention so far.
Hello, my name is Raphael and I'm an engineer at TIL Energy. In the first part of this video, we have learned what a FMU is and how to export a FMU from a Daimler model. In the second part, I'm going to show you how to use FMUs for model-in-the-loop, software-in-the-loop and hardware-in-the-loop applications. Let's start with a quick overview of model-in-the-loop, software-in-the-loop and hardware-in-the-loop and how they can save a lot of time and money in controller design.
Traditionally, you might design and code a controller, then test it on a physical test bench. However, this method is slow and expensive. Test benches take a lot of time to set up and maintain. Plus, any changes to the controller code mean you must redeploy the entire controller executable each time, which isn't efficient. In contrast, model-in-the-loop, software-in-the-loop, and hardware-in-the-loop approaches make testing and designing controllers much easier and faster right from the start. In engineering, systems often have two parts: the plant model, with its physical characteristics, and the controller. Instead of using a physical test bench, we connect the controller model with the digital twin plant model and simulate the entire system. This is called model-in-the-loop, or short MIL. Once we find a good design, we export the controller to a software model and test it again, called software-in-the-loop, or SIL. Finally, we install the controller code on physical hardware, like a microcontroller board, known as hardware-in-the-loop. For hardware-in-the-loop, the plant model and the controller must communicate in real time using a special computer like a speedcode test system. How do FMUs fit into model-in-the-loop and hardware-in-the-loop frameworks? For the plant model, we use the heat pump model created with the TIL library in Daimler. The TIL library, based on 20 years of engineering know-how, is ideal for modeling and simulation of thermal systems. Together with Daimler as a powerful simulation environment, physical relationships can be modeled acausal. In other words, there's no need to tediously transform balance equations, and the object-oriented language makes the model easy to understand. The controller is modeled in MATLAB Simulink. Simulink offers many great features for controller development, such as state machines optimization and code export to various hardware targets. Hence, by combining a plant model created with TIL and using Simulink for the controller, we get the best of both worlds. The functional mockup interface provides the coupling between both. In the next step, we take a look at the Simulink implementation. In this Simulink window, we prepared a setup where we connected a plant model to a controller model. Now, the FMU comes into play. We can easily import our plant model as an FMU into Simulink and link it with a controller model. The controller's job is to manage a specific task for our heat pump, defrosting. Let me give you a quick introduction to what defrosting and defrosting mean in the context of heat pumps. In a typical heating setup, the condenser is inside the building and the evaporator is outside. Cold refrigerant flows through the evaporator, absorbs heat from the outside air, evaporates, and then transfers this heat inside while condensing in the condenser. If the evaporator temperature drops below 0 degrees, moisture from the air can freeze on it, forming an ice layer. This ice reduces the system's efficiency by decreasing the heat transfer. A simple defrost method involves reversing the cycle briefly. A 4-way valve switches the roles of the condenser and evaporator using heat from the inside to melt the ice outside. But how do we know when to trigger defrosting? Let's design a defrosting controller. When the evaporator's heat transfer drops, it means ice has formed. We can estimate the heat transfer coefficient UA by dividing the heat flow by the temperature difference. We will compare this value to the heat transfer after the last defrosting, UA defrost, and trigger defrosting whenever UA is much smaller than UA defrosting. To keep it simple, defrosting will run for a fixed time, which should be enough to melt all the ice. Let's switch back to our Simulink implementation. In this Simulink window, we prepared a controller model. We use Simulink Stateflow to easily translate our controller concept to a state machine. Here we can see the different states, like heating or defrosting, switching based on our conditions. I added an immediate state, heating equilibration, to stabilize the system for a bit after defrosting before returning to heating. The inputs of this controller connect to the heat pump sensors and the outputs to the actuators. Now, let's simulate the plant model together with the controller. The simulation runs in Simulink and outputs the results to Dave, a visualization tool adapted to the TIL library. The plots show the log pH diagram, the ice mass, and the reverse cycle status. Over time, the ice mass increases slowly. Defrosting melts all the ice, and after defrosting, the ice mass increases again, such that a periodic pattern emerges. Our defrosting controller seems to work, but how robust is it? To test robustness, we define test cases based on how the heat pump should operate in different conditions. Real-world experience helped to identify rare but important fringe cases that must be handled appropriately. Let's consider a simple test case. Increasing the water return flow temperature by 30 degrees. This could simulate different temperature needs for floor heating or hot water. For example, if we turn off the floor heating to take a shower. In Simulink, we apply a temperature ramp to the return flow and restart the simulation. In Dave, this plot shows the water return flow temperature. Surprisingly, the defrosting controller triggers as soon as we encounter our temperature ramp. It seems the evaporator heat transfer decreases, causing defrosting. But how does a change in the water flow temperature in the condenser affect the evaporator's heat transfer?
Troubleshooting this issue on a physical test bench would be difficult, but our simulation model lets us investigate what happens in detail. Let's take a look at the log pH diagram when we apply the temperature ramp to understand what's going on. Higher water temperature requires a higher refrigerant temperature in the condenser, which means higher pressure and more refrigerant gas. This gas needs to be evaporated from the liquid in the separator using energy from superheated refrigerant from the evaporator. This point here we can see the superheated refrigerant exiting the evaporator. Lowering the evaporator pressure increases the superheating temperature, but this reduces heat transfer, wrongly triggering the defrosting controller. Going back to Simulink, in Stateflow, adding a simple timer to the defrosting controller can prevent premature triggering during these transient changes. In this last section, we finally run our model on a real-time hardware platform to enable hardware-in-the-loop tests, the SpeedGoat test system. What is SpeedGoat? We would like to let Christoph Hahn from SpeedGoat introduce you to the system.
Hi, my name is Christoph Hahn and I am Head of Technical Marketing at SpeedGoat. SpeedGoat test systems enable engineers and scientists to test embedded controllers and prototype complex control designs. SpeedGoat test systems seamlessly integrate with Simulink and allow engineers to test continuously, automate testing, remain innovative, and comply with requirements. Together with TLK Energy, we provide our joint customers with a solution for developing and testing control software for thermal systems like heat pumps. TLK's thermal system simulation models run on powerful, scalable SpeedGoat test systems. Their wide range of I/O connectivity allows users to connect controllers, sensors, and other data inputs and outputs, while the simulation models run in deterministic real time. Control designs and controllers tested using SpeedGoat systems drive electric vehicles and aircraft, power industrial machinery, operate medical devices, and manage electrical grids and renewable energy sources. So SpeedGoat test systems are well established in all major industries. Therefore, we are glad to support TLK in enabling this testing solution for thermal systems such as HVAC and P2X processes for our joint customers.
Simulink integrates seamlessly with the SpeedGoat platform, allowing us to run simulations in real time with just a few steps. In a typical setup, controller and plant model run on two different SpeedGoat devices, which can be connected via various communication protocols. We switch to the real-time tab, connect to the target PC, and run the simulation as simple as before by clicking Run. Simulink compiles and runs the code for the selected hardware targets. Here we can see that our model runs indeed in real time. The bottom plot shows so far no indication of any overrun. An overrun occurs whenever the simulation runs slower than real time. The models for the controller as well for the plant must be optimized to prevent those overruns. Hence, our model is optimized enough to enable a real-time simulation. I hope that I could give you a good overview of model and hardware in the loop and its potential for testing thermal systems. Thank you for your attention.
Yeah, so here again with the live part. To sum up the technical things you've seen, I also want to show what we offer, so what you exactly get from us if you want to get started with model-based control development. And maybe the easiest way to find us for this topic is just to use Google and enter HiL TLK. Then there should be, depending on your country, whatever, there should be some top entries about it. So we have two pages. One is describing our services That's this one, and another one is a blog article which partly reflects some parts of this webinar. So I want to show you our service offering shortly. Let's switch to English. You can see here, some references. So already have learned we are official partners from Speedcode, but also from MassWorks, and also from DSpace, which is some kind of Speedcode competitor in that sense. And yeah, you also see some reference clients where we have done projects in this area, which are where we can talk about. It's Volkswagen, Weiland, Viessmann, and Emerson. It's now named Copeland, so we should change this logo. Yeah, you can read through this. It's kind of describing our offering, the benefits again of hardware in loop. If you want to reach out to us, learn more, we are happy to discuss it. You could use this form here, or you can also directly book a meeting. Just feel free to contact us if you're interested to learn more about the specific topics. And yeah, then we will start with the interactive question session.